Hello. A few weeks ago I made a video talking about different image types, but I ignored a whole lot of details. So this video, and a few coming later, will be about one image compression type only. Today it'll be about the Jpeg compression algorithm, or DCT, or discrete cosine transform. If you know DFT, or discrete Fourier transform, it's the same thing but without the sine component. Let's start simple. Audio. DCT can be used in a lot of things, but audio is the simplest. I'm going to be using 3 Blue 1 Brown's explanation of DFT. Here's an A. It's 440 Hz, so if you plot the sound from this A, you get this kind of wave. It goes back and forth 440 times a second. Now here's a D. This instead is 294 Hz. Once again, if you plot this D, it'll go back and forth 284 times a second. Now if we play these two at the same time, we get another wave. But notice how it doesn't look the same as the other waves, because at any point in time, the difference is the sum of the other two waves together. Sometimes there'll be peaks, sometimes they're going to cancel out. If we add more notes, the resulting wave will be more complicated. Now let's say we forgot the notes we used for this wave. How do we get it back? First, let's take a raw wave. For simplicity, this wave is 3 Hz. Next, let's draw this wave in a circle. There's an arm in the middle drawing out the wave, low points closer to the middle, high points closer to the edge. But we're able to choose how quickly this circle spins. Next, let's make a center of mass in the circular wave. It'll normally stay near the middle, but when the points are closer together, the center of mass is far out. Let's plot the center of mass. We're only keeping track of the x coordinate. If you want a proper DFT algorithm, you're gonna have to worry about also the y coordinate. Since it's not proper DCT, we're not worrying about that. As you can see, it starts high, has chaos, then spikes at 3 and more chaos. If we do the same thing with a wave but it's 2 Hz, it does the exact same thing but spikes at 2. If we add the two waves, we get something like we had earlier. If we do the same thing, notice how there's now 2 spikes, a spike at 2 and a spike at 3, which happens to be the 2 waves we put in. Now we already have a start on DFT. This isn't a full transform for multiple reasons like I said earlier. But how do we put this into DCT? First problem. The method that we're using detects how strong the sine and cosine component is. That's because the full DFT represents a signal as both sine and cosine waves. In many real signals, especially images, we don't actually need both. So how do we remove the sine component? The trick is surprisingly simple. We mirror the signal. Let's say we start with this wave. Instead of wrapping it around a normal Fourier transform, we reflect it. This mirror signal is perfectly symmetric. Because of this, sine components are automatically 0. Only cosine components remain. Now, when we measure the frequencies, we only need cosines, and that measurement is the DCT. But Jpeg doesn't compress sound, it compresses images. Images are 2D signals instead of a 1D signal. The idea is the same. We want to represent a signal, a block of pixels, as a sum of cosine patterns. We start by breaking the image into 8x8 blocks. Each block contains pixel brightness values. For convenience, Jpeg shifts these values so they're centered around 0. This is like doing the same frequency analysis we did for audio, but now in 2D. First, we detect horizontal variations across each row, then we detect vertical variations down each column. The result is 64 coefficients, each telling us how much specific 2D cosine patterns exist in the block. The top left coefficient is the average brightness, low frequency, and the bottom right coefficients represent very rapid changes, high frequency like checkerboards. but most of the energy is in low frequency coefficients, top left, and high frequency coefficients, bottom right, are very small. First, quantization. Jpeg reduces the size of each block by dividing each coefficient by a predefined number from a quantization table, then rounding the result. The low frequency coefficients get small divisors, become mostly preserved. High frequency coefficients get larger divisors, often become 0. By doing this for all 64 coefficients, many of the high frequency values become 0, which is great for compression. This is the step where image detail is reduced. This is what makes Jpeg lossy. Next, zigzag ordering. Once the block is quantized, Jpeg reorders the coefficients in a zigzag pattern. Starts from the top left, low frequency, moves diagonally to the bottom right, high frequency. Most zeros end up grouped together at the end. Makes the next step, Huffman coding, much more efficient. Lastly, Huffman coding. Finally, Jpeg compresses the 1D sequence of coefficients using Huffman coding. Huffman creates a tree where most common numbers are near the top and rarer numbers near the bottom. To encode a number, go right, add 1, go left, add 0, until you reach the number. By the end, frequent numbers get shorter codes, rare numbers get longer codes. This reduces the total file size significantly without losing any additional information. Now that's it. That's the full Jpeg encoding this time. Hopefully the next one you'll see is about PNG. I'm not exactly sure, but that's what I'm planning. Bye.